class. Today we're going to be talking about section 4.1 for college algebra, which is introducing exponential functions. We're going to look at the definition of an exponential function and a little bit about graphing as well. So an exponential function, kind of in general, is a function where the variable is in the exponent. So we've done polynomial functions where we have x squared or x cubed, where x has an exponent. This is a little different because x, our variable, is going to be the exponent. So for example, f of x equals 2 to the x. Yes, this is an exponential function. We have a base of 2 and the exponent is x, which is our variable. 1 to the x is not actually an exponential function. It looks like it, but if we graphed 1 to the x, 1 to any exponent is just going to be 1. So this is actually just a constant function, y equals 1. So be careful. They'll try to kind of throw you off there. X squared, no, is not an exponential function. That is a quadratic function. E to the x, yes. E is a number that is approximately 2.71 or so. So this is... we have to be careful, kind of like pi. Pi is a number, 3.14. E is also a number that's used frequently. Negative 10 to the x. So this one is not an exponential function. So our definition is a little bit more than just x in the exponent. The base has to be greater than 0 and it can't be 1. If the base is, so my base is less than 0 here, which is a problem. If the base is negative, we get this really weird graph thing that like looks like this, sort of. It like keeps going with this pattern. And actually it's even more complicated than that. If you end up with like exponents that equal even roots, then you have imaginary numbers and it gets really weird. All right, so f is an exponential function. It's 2 to the x. B is greater than 1, so my base is greater than 1. And the x plus 1 just translates into a horizontal shift, 1 left from y equals 2 to the x. So it is exponential, it's just shifted over 1. X to the x is interesting, but it is not an exponential function. So our base has to be a constant value. All right, and then our last one, h, yes, this is an exponential function. We have a base that's greater than 0 and it's not equal to 1. And not equal to 1, it's totally fine. We have a constant base, x is in the exponent. We have a bunch of transformations happening here, but that's an exponential function. All right, so example 1, we have an exponential function, f of x equals 42.2 times 1.56 to the x power. Models the average amount spent in dollars at a shopping mall after X hours. What is the average amount spent to the nearest dollar after 4 hours? So they want X to equal 4, and this is just kind of one of those problems where we plug it in. I do want to talk about order of operations really quick. So if I plug it in, and I want you to show that work, I know that you're going to be using your calculator, but I want to see what you put in your calculator on your papers. Always do... So order of operations, we do the part with the exponent first. Now your calculator will most likely, if you type it all in, do it right for you. Just be careful not to do the multiplication first and hit enter and then the exponent. It's not going to work out. So you should get $249.93, but it said to the nearest dollar. So that's going to be approximately $250. All right, let's talk about graphing. So we're going to make a table of values and graph f of x equals 3 to the x. So let's look at what that's going to look like. I'm going to use the values of x, -2, -1, 0, 1, and 2, just to see what happens kind of at 0 and then little positives, little negatives. So if I have, let's start at 0, 3 to the 0 power, anything to the 0 is 1. So just a quick little rule, anything to the 0 power equals 1. Doesn't matter what that value is, it's going to be 1. 3 to the 1 power is 3. 3 squared is 9. Now what happens if I have negative exponents? 3 to the -1, 3 to the -2. Well, a to the -n power is 1 over a to the n. So it kind of flips it into the fraction where now that value is in the denominator, and then the exponent turns positive. So this is going to be 1/3, and this is going to be 1/3 squared, which is 1/9. Now I can find more values, but I think that this will probably be good. Let's graph this. So 0, 1. We have 1, 1, 2, 3. My 2, 9 isn't going to fit on my graph, so I don't need to worry about it. -1, positive 1/3. -2, positive 1/9. And if we think about as we keep going bigger, let's think, 2 is up at 9, 3 is going to be up at 27. It's going to get really big really fast. So when you draw this, couple things, be careful. Don't cross that vertical boundary where x is 2 unless you're actually crossing it at 2, 9. So one thing to be careful of. Now think about as we go to the left. So if I get smaller and smaller and smaller values of x, I'm just going to get smaller and smaller and smaller fractions. There's still going to be positive fractions, which means this thing is going to get infinitely close to 0, but never actually equaling 0, and it's never going to go negative, which means we have what we call an asymptote. We have a horizontal asymptote. I'm going to draw it in orange here. So I have a horizontal asymptote at the line, so this is horizontal asymptote at the line y equals 0. So if you've never seen an asymptote before, a horizontal asymptote denotes the end behavior of our graph. So, and actually let's write that in here. So end behavior as x approaches infinity, where does f of x go? So as x goes all the way to the right, where does our function go? Well, in this case, it goes up to infinity because it's exponential growth. But as x approaches negative infinity, f of x, the y value, so as we go to the left, which way are the y values going? Well, they're going closer and closer to 0. That is connected to our horizontal asymptote. So the horizontal asymptote tells us where the ends of the graph, sometimes it's both ends, sometimes it's only one end, but where the ends of the graph are going. Now our domain is going to be, sorry about that. Our domain is going to be all real numbers, or negative infinity to infinity. Our range is not, though. Think about, so domain is how far left, how far right are we going to go? That thing's just going to keep going. If we think about the range, how far down and how far up is this thing going to go? Well, it's only going to go as far down as 0, and it actually won't even ever get to 0. So we're going to use a rounded bracket instead of a square bracket. It is going to go up to infinity. Or you can write it as y is greater than 0. That's fine too. This is an exponential growth function. Decay means as x approaches infinity, it's going to be going down. So it'll be going the other direction. All right, so there's our first example. Let's look at the next page here. So we have a similar function, but f of x is 1/3 to the x. So let's kind of do the same thing. I'm going to speed up a little bit. So -2, -1, 0, 1, 2. 1/3 to the 0 power is still 1. Anything to the 0 is 1. 1/3 to the 1 power is 1/3. 1/3 squared is 1/9. 1/3 to the -1. So now if you have a fraction, a over b to the -n, what that does is it flips your fraction over and becomes a positive exponent. So these are just exponential property rules. So 1/3 to the -1 is going to end up being 3/1 to the +1. So we flip that over, which is 3. And then similarly, 1/3 to the -2 ends up being 3/1 to the +2, which is 9. So we get the same values we did in the last problem. They're just switched or flipped. So if x is -2, y is going to be up at 9. Which is off my graph. If x is -1, I'm going to have it up at 3. 0, 1 is still there. 1, 1/3, 1/9. So you can see this has a very similar shape to the last one. But this time, as x approaches infinity, whoa, I kind of got off my graph there. Sorry about that. As x approaches infinity, it's going to get closer and closer to 0. So it's It's actually more like a reflection across that y-axis from our growth. This is what we call an exponential decay function. We have the same horizontal asymptote because the end behavior, even though it's the other end, so horizontal asymptote is still y equals 0 in this case. The end behavior, even though the end has switched, it's still one of the ends is going towards 0. So as x approaches infinity, f of x is approaching 0. There's that horizontal asymptote. As x approaches negative infinity, so as we go to the left side of our graph, as we trace our function into the left side, f of x is going to be going up to infinity. So our end behavior has switched for decay. Our range is still the same from 0 to infinity, and our domain is still the same. So, negative infinity to infinity. So the only thing that's really changed is the end behavior has switched to the opposite end of our graph. All right, let's look at an example with a couple transformations. So this is going to be, and now I'm going to do this a little differently. I think every teacher does graphing transformations a little differently. I'm going to make an XY table with just the parent function 2 to the x, because it's a little easier to manage. So 2 to the 0 power is 1, 2 to the 1 power is 2, 2 squared is 4, 2 to the negative 1 is 1/2, and 2 to the negative 2 is 1/4. Sorry if I'm going a little too fast. Don't want the video to be too long. Now, the x minus 1 and the minus 3 means I'm going to be moving these points 1 to the right and 3 down. So the way I like to do it is I like to do this movement and put a star on my graph. So if I go 1 to the right and 3 down, I'm going to just put like a little star on my graph there. Now, I'm going to do these movements from the star. So if I go -2 from the star, I'm going to go up a quarter. So -2 up a quarter, -1 up a half, 0, 1, 1, 1, 2, and 1, 2 to the right from the star is going to be up 1, 2, 3, 4. And actually, I think I can fit one more. 3, so 2 to the third is 8. So if I go over 3 from the star to the right, 1, 2, 3, I go up 1, 2, 3, 4, 5, 6, 7, 8. I always try to fit as many points on my graph that'll fit so that I can have a perfect graph, or at least as perfect as I can. Now, if we think about what's going on here, if I draw connect my dots here, try to make it good. Think about what's going to happen as I keep going to the left. It's going to get closer and closer and closer to our horizontal asymptote, which now has been shifted down to y equals -3, y equals -3. So I need to complete my graph and make sure that this doesn't cross that horizontal asymptote. Now, later on, by the way, just a little information for you, when we get into harder graphs, things like that, maybe in pre-calculus, you will see functions cross a horizontal asymptote, and that's okay, because the only point of a horizontal asymptote, the only purpose is to denote the ends of the end behavior of your graph. So in the middle, it can actually cross if it wants to, but in this case, it never will. So here's our function. Notice where the star was, where I went over 1 to the right and 3 down. It wasn't a point on my graph. So I put a star because it doesn't necessarily mean it's a point. It's just my shifted origin. And if we think about our other functions, they didn't go through the origin, so they shouldn't go through your shifted origin. All right, my domain is still all real numbers. It will be for any exponential function. My range now is from -3 to infinity, or you can write y is greater than -3. My end behavior as x approaches infinity, as we go to the right side of the graph, f of x approaches infinity. And as x approaches negative infinity, f of x approaches -3 for our horizontal asymptote. This is a growth function. And how did the transformations change the above information? Well, they just shifted our 2 to the x, 3 down, and 1 to the right. So it's just a shift of that function. All right, let's talk a little bit about the number e. So we have what we call the natural base e. is about 2.718 or 2.72 if you want to use just a couple decimals. It's defined as the value of 1 plus 1 over n to the n power as n approaches infinity. So we could talk about limits, but I think that's a little out of our college algebra course. You'll talk more about limits in calculus, which is really fun. I like limits. All right, let's look at what e to the x looks like when I graph it. So e, remember e is just a number 2.718. So if I make a table of values, x, y, -2, -1, 0, 1, 2, don't let the letter e scare you. It's just 2.718 to the 0 power is still 1. 2.718 to the 1 power, 2.718 squared, 2.718 to the -1, 2.718 to the -2. So you can plug these in your calculator. You're just going to get decimals, and it's not as easy to graph, but it's still all right. We end up with the 0.01, 1, 2.7-ish, and I'm just going to kind of draw a quick sketch of this one, just so we can talk about the fact that it's really the same as the others. It's just slightly different points. 0, 1 is still the same point, but the other ones are slightly different. Our domain is still the same. Our range, it hasn't been shifted, so it's still the same. I still have a horizontal asymptote, and I want you to draw the horizontal asymptote on your graph. If you do not draw it, I will take off points. So this is at y equals 0 because it hasn't been shifted up or down. This is a growth function because our base, which is e, our base is e, which is greater than 1, which makes it growth. And our end behavior as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches 0 because of our horizontal asymptote. All right, I'm going to skip the next example. You guys can look at your note in our calendar that's already filled in, and there is an E button on your calculator that you can use to make that easier. Let's go down here to the compound interest formula. So I love interest rate formulas. They're so much fun. Now our compound interest formula, and I do want you to memorize these. We have A, which is the balance that we have kind of at the end, our resulting balance, equals P, our principal amount or our starting amount, times 1 plus R, our interest rate in decimal form, over N. And N is the number of times that it's compounded each year. And then all to the exponent of N times T, which is our number of years. Now, if it's continuously compounded, what that means is it's compounded infinitely many times per year, just continuously. We can't really put infinity in for n, so we need a different formula, and that's where e comes in handy. We have p times e to the rt. So let's look at this example, and then this is our last example for today. You decide to invest $8,000. So that is your principal amount, $8,000 for 6 years. So T is 6. And you have a choice between two accounts. So we're going to versus here. Okay. You first one pays 7% per year. So your annual interest rate is going to be 0.07. So transfer or convert that percentage to a decimal. Compounded monthly. So if it's compounded monthly, then how many times per year is that compounded? It's 12 times per year. And then the second one, so I still have $8,000 for my principal. I still am doing 6 years, but the interest rate is different. It pays less interest, 0.685. Oops, nope, that's wrong. 0.0685. We moved that decimal over 2 places per year, and it's compounded continuously. So we use E, since it's compounded continuously, we use the E formula. Which one's a better investment? So one of them has a higher interest rate, which usually means you get more money, but it's compounded less times per year. One of them has a lower interest rate, but it's compounded more times per year. So let's see which one is the better option. By the way, not all banks are created equal. Do some research before you choose which bank to go with. Math is useful. All right, so let's look at this. So A equals my $8,000 times 1 plus 0.07 over 12 to the power of 12 times 6. And make sure when you put it in your calculator, you use parentheses. Parentheses are your friend. If you forget parentheses around the 12 times 6, you will get the wrong answer. So be really careful. You should get, let's see, 12160.84. So $12,160.84. Good luck finding a real bank account that pays 7% interest per year, but it's fun to play with the numbers. All right, so let's look at this one. We're going to use slightly different formula. So this one was a equals p times 1 plus r over n to the nt. This one's going to be a equals p times e to the rt. So a equals my $8,000 still, times e to the power of 0.0685 times 6. So when we plug that in our calculator, we get 12,066.60. So we didn't quite get as much money there. So let's write our thing here. We've got a 7% compounded monthly is better for 6 years. All right, and that's it for today's lesson.